Hello and welcome. Today we're going to dive into a really powerful, kind of hidden principle that shapes almost everything around us. I'm talking from the tiniest ant colony all the way up to the massive infrastructure of the internet. It's this force that has no leader, no grand master plan, and yet it builds worlds of just staggering complexity. So let's pull back the curtain on these unseen architects. Okay, I want you to picture this. You've got thousands of birds in a flock, twisting and turning through the sky like they're a single living creature. They ripple, they contract, they expand. It's a perfectly synchronized ballet in the air. So you have to wonder, who's conducting this whole masterpiece? Who's giving the orders to turn left or dive or swerve all at once? Who is in charge here? Well, the answer is both super weird and incredibly elegant. No one's in charge. There's no leader. No central choreographer calling the shots. This amazing order just arises spontaneously out of chaos. It's a phenomenon called emergence, and it's the secret architect of our world. So how is that even possible, right? How do you get intelligent, coordinated behavior without anyone actually being in control? Let's start by peeling back that first layer of the mystery. Here's the key thing to get your head around. Complex patterns, the really big ones, are almost never designed from the top down. They emerge from the bottom up. And it all happens because each individual in the system, every bird, every ant, every fish, is just following a few incredibly simple rules based only on what's happening right next to it. So let's see how this actually plays out in nature. We're going to look at a few examples of how different species use their own unique set of simple rules to pull off some pretty incredible collective feats. You know, a school of fish moves with this fluidity that just seems almost magical. How do they do it? Well, besides just using their eyes, fish have a kind of superpower. It's called the lateral line. It's this whole sensory system with thousands of tiny receptors that can feel the absolute slightest changes in water pressure. It gives each fish a real-time map of its neighbor's movements, letting it perfectly match what they're doing. It's a simple local rule. Just react to the pressure waves next to you. That creates this stunning, cohesive group. Okay, but what if you need to coordinate with others and you can't see them or sense them directly? Well, nature has a brilliant solution for that too, and it's called stigmergy. You can think of it like leaving messages for your colleagues by changing something in the office, like putting a note on a whiteboard. It's a way for individuals to communicate across time and space without ever having to meet face to face. The classic example here, of course, is an ant colony. When an ant finds food, it leaves this chemical trail of pheromones on its way back to the nest. Other ants smell this trail and, naturally, they follow it. Now, here's the really clever part. The ants that happen to find a shorter path get back to the nest faster. That means they can make more round trips in the same amount of time. Their shorter trail gets reinforced with more pheromones, more quickly, making it stronger and way more attractive to other ants. This whole thing creates a powerful feedback loop that very quickly guides the entire colony to the most efficient path, all without a single map or a single leader giving directions. It's amazing. But what about more complex decisions? Birds do something that's, well, it's fascinatingly different. When a flock of pigeons takes off, they circle around for a while. You might think they're all kind of voting on the best direction to go, but research shows that's not what's happening at all. They're not averaging opinions. Instead, they're in a consensus-building process. But it's not to decide the route. It's to democratically elect temporary leaders for that specific flight. They're literally building a consensus on who to trust, and only then do they follow. It's a much more sophisticated participatory kind of leadership that just emerges from the group. Okay, and this is where it gets really powerful. For decades, computer scientists and engineers have been looking at these natural systems and thinking, hey, we can use that. They've taken these biological strategies and translated them directly into code to solve some of our most complex problems. So let's go back to our ants. Their algorithm is so simple and elegant. Follow the chemical trail, and the strongest trail is probably the best one. It's just a brilliant solution for finding the shortest path between 2 points. And here is how that gets translated into an algorithm. Now, don't worry about the math. Seriously, just focus on the ideas. They create a variable for the pheromone trail to represent its strength. They add heuristic info, which is just a fancy way of saying a rule of thumb, like prefer shorter paths. And then, here's the genius part. They include evaporation. This makes old, inefficient trails fade away so the system doesn't get stuck on a bad solution. It is a direct one-to-one translation of nature's logic into code. Now, ant colony optimization is part of a much bigger field called evolutionary computation. This is an entire branch of artificial intelligence that's all about creating algorithms that mimic nature's problem-solving toolkit. You know, evolution, selection, mutation, the whole shebang. It's about letting the best solutions evolve on their own, rather than trying to design them perfectly from scratch. So, let's take a look at how these ideas are shaping some of the most advanced technology we use every single day. We're moving from just nature-inspired algorithms to building entire technology infrastructures that behave like living ecosystems, especially in the cloud. So today, most big cloud systems work with a top-down command and control model. You have a central brain, like Kubernetes, that tells all the other parts what to do. But there's this radical new vision inspired by swarm intelligence. What if we just got rid of the central brain? What if the cloud was made of countless autonomous cells that could self-organize to get work done? The intelligence would emerge from the bottom up. To see how this could work, we can apply the classic rules of flocking. Let's start with Rule 1, separation, or don't crowd your neighbors. Imagine if each little part of a cloud service could sense when its neighbors were getting overloaded. It would simply steer its work away to a quieter area. If every single part is following this one simple rule, the entire system would just balance itself automatically. No central load balancer needed. Okay, next up is alignment. Steer toward the average direction of your neighbors. In the cloud, this basically encourages collaboration. Services working on similar tasks would naturally start to sync up their efforts, kind of like paddlers in a canoe all matching their stroke. And all of a sudden, complex data pipelines can just form on their own, without any master blueprint telling them how. And the final rule is cohesion. Stick together. For cloud services, this means that all the different parts of one application feel a sort of natural pull toward each other. They automatically form these tight-knit clusters for redundancy. So if one part fails, the others are right there, ready to take over. The system becomes self-healing. Now look, there's always a fundamental trade-off in any huge distributed system. It's called the CAP theorem. And basically, you can't have everything be perfectly consistent and up-to-date everywhere all at once. It's impossible. Top-down systems really fight against this reality, but emergent systems, they embrace it. They accept that information is going to ripple through the network over time, just like a pheromone trail, and they aim for eventual consistency instead of impossible perfection. You know, this whole way of thinking about bottom-up rules and emergent results, it isn't just for birds and computers. Understanding emergence is actually a critical skill for navigating our own complex world, from our jobs to our organizations. For years, when something went wrong, we'd use what's called root cause analysis to find the one broken part, the single person to blame. But in a complex system, that whole approach just falls apart. Big failures are almost never caused by one single thing. They are emergent properties of many different factors, all interacting in unexpected ways. We have to stop looking for the one broken piece and start trying to understand the whole system. So how do we actually do that? A fantastic, practical way is the theory of constraints. It gives you 5 focusing steps. First, you identify the single biggest bottleneck in your entire system. Second, you exploit it. Make sure that bottleneck is running at 100%, never sitting idle. Third, you subordinate everything else. The whole system's only job now is to support and feed that one constraint perfectly. Only then, if it's still a problem, do you elevate it by adding more resources. And finally, you repeat the whole process, because once you fixed one bottleneck, a new one has just emerged somewhere else. It's this continuous cycle of improvement that forces you to think about the whole, not just the individual parts. And that really brings us to our final thought here. We've seen how leaderless, intelligent systems can emerge from just a few simple local rules. It really makes you wonder, doesn't it? What are the simple, unseen rules that are shaping the complex systems in our own lives? The culture at your company, the dynamics of the global economy, the flow of ideas on social media. What if we could actually identify those rules? And what if we could we change them for the better? That right there is the power of thinking in systems. Thanks for joining me.